For the second RF pulse, I call it the repetition time, or TR. Now, if I say that I will apply the first pulse, which is the 90-degree pulse, and wait a long time before the second one, what will essentially happen? Both will ultimately return to their original state, and the signals will drop again and become similar. The goal is to create a difference in magnetization between fat and water. How do I achieve this? You should not wait too long, because if you do, both will return and become the same. No, I want to wait a short time. That's why they say if you choose a long TR, you will significantly reduce this gap and the difference. Reduce the difference, or reduce the variation between the customers and the water. It will significantly decrease. It will decrease a lot. You don't want that. You want to enhance it, so you choose to maximize this difference. They call this first pulse the initial pulse because it is meant to create an excitation and then drop the water signal at the XY plane. Then we apply a 90-degree RF pulse and run the sequence normally. Is there a problem with this T1 weighted image? There are no issues. The fat appears more bright, while the cerebrospinal fluid, for example, appears more dark, resulting in your T1 weighted image. Essentially, the fat appears more bright, while the cerebrospinal fluid, for example, appears more dark, resulting in your T1 weighted image fundamentally. In essence, the fat appears more bright, while the cerebrospinal fluid, for example, appears more dark, resulting in your T1 weighted image inherently. Basically, the fat appears more bright, while the cerebrospinal fluid, for example, appears more dark, resulting in your T1 weighted image. T1 weighted image. Okay? So here is the difference. The difference is between fat and water, or cerebrospinal fluid, CSF, for you. The T1 weighted image shows more bright areas with high signal intensity, intermediate signal intensity, low signal intensity, and black areas like air, calcium, cortical bone, and rapidly flowing blood, for example. The plaque, like air, calcium, cortical bulbar, and rapidly flowing blood, as well as ligaments, muscles, and tendons, all of these are protein tissue. The complex cysts and synovial fluid appear with intermediate signal intensity, which is similar to the signal intensity of fat and blood. This is relevant in the T1 weighted image. Here is the first RF pulse, and here is the second RF pulse, and this is your TR. Now, is the TR for the T1 weighted image short or long? We agreed that its range is from 300 to 700 milliseconds. Therefore, the echo time, which is the recording time, will also be relatively short because you will give the RF pulse and start receiving the signal. So the echo time will be relatively short as well, ranging from 10 to 30 milliseconds. Now, as you can see, I hear this is the T1 weighted image sequence I am performing, and this sequence is called spin echo. Why spin echo? The term spin echo is used because you are relying on taking a signal based on the spin. What does this mean? I will tell you now. When we talk about T2, which is the decay of the signal, what do you find? When I stop with the RF pulse, the protons start to disperse from each other and begin to lose the transversal magnetization, as mentioned earlier. When examining the transversal magnetization, you find that the decay of water, for example, takes longer than that of fat. At that time, if you come to register your signal with a short echo time, the difference between fat and water won't be significant, so you should choose a long echo time to register your signal. This way, the cerebrospinal fluid will appear bright, as you can see here, while the fat is not bright, as you can see here. So, the T2 weighted image is dependent on T2, which is 37% of the decay, or the value of transversal magnetization, and it relies on the echo time. Therefore, the T2 sequence is highly dependent on the value of the echo time. If I choose long echo time, then I must also choose long repetition time, TR. Now, why do I also choose long TR in the T2 sequence? The reason is that you choose long TR so that at this time, the longitudinal components return to be equal. The difference primarily depends on the difference in transversal magnetization, not on longitudinal magnetization. That's why in the T2 sequence, I choose long TR to eliminate the effect of T1 and the influence of longitudinal magnetization, and I choose long TE to maximize the difference in transversal magnetization between the water and fat, or CSF and fat. In the T1 sequence, a short repetition time is chosen to maximize the difference between fat and water in the transversal magnetization, and a short echo time is selected because of its benefits. We have a slight difference between cerebrospinal fluid and fat in the medium magnetization, so you are removing the medium magnetization in the short time and removing the medium magnetization in the short time. Is this dangerous? Right? Very good. The challenges are based on the repetition time. All right. So the protons are in the MXY dimensional plane, and they are significantly affected by the powerful and strong, constantly varying magnetic field of the imaging device itself. The magnetic field of the device will never be absolutely and perfectly homogeneous. It will always have some degree of inhomogeneity. The decay of MXY is considerably and substantially faster than the relaxation of T1, meaning that the decay of MXY is quicker than the T1 constant for almost all materials when compared to water. The decay of MXY and the relaxation of MZ are approximately equal in rate. So why is the T2 constant always faster? Why does this rapid decay occur? Because the protons in MXY are under the influence of the magnetic field, which is the device's magnetic field. The magnetic field of the device is never just a simple and straightforward 1 Tesla. There must be some inhomogeneity present in the magnetic field. Protons, when grouped together in a magnetic field, are significantly affected by this difference in the main homogeneity of the field. This causes each individual proton to rotate or be influenced by different strengths of the magnetic field. As a result of these varying influences, they begin to rotate at different speeds over time. This variation in rotational speed leads to a phenomenon known as defacing, which in turn accelerates the defacing process. The defacing process is crucial in understanding how magnetic fields interact with atomic particles, and it has significant implications in fields such as nuclear magnetic resonance and other scientific applications. Look here, this is the proton, like this, all in the X and Y. Look at what happens in the relaxation. This difference occurs because of the inhomogeneity in the magnetic field, and as a result, it increases. There's something else to consider. Look here. The protons have now moved apart from each other. This separation, which we are observing, that occurred in the protons is due to the lack of uniformity in the magnetic field in the surrounding environment. Okay, that's number one. Number two, the proton itself is affected in a significant way by the magnetic force in its vicinity. This magnetic force will have an impact on the neighboring proton, and that neighboring proton will have an impact on the one next to it, leading to a change in the magnetic field between the protons in a chain reaction. This leads to a gradual but noticeable acceleration of loss of phase coherence, because each proton will take a different speed, and over a period of time, they will start to experience loss of phase coherence. This makes the process of decay of the MXY component quick and pronounced in nature. So now I have a challenge with maintaining homogeneity. What I call the magnetic field, which is stability. Okay, the homogeneity or stability effect on protons, I want to eliminate it, and I want to do the elimination for it, so that my image depends only on the T2 constant of the tissue of the water, not on the diffusion that occurred. So, I have a curve that appeared, the initial curve which I call T2 star, which is the shape of MXY, and it undergoes decay along with the effect of inhomogeneity in the magnetic field. The magnetic field I described earlier. Now, when I remove their effect, the curve appears in this shape and takes longer time. So I called it T2 sequence. So, what do you want to do? I want to eliminate the diffusion that occurred. How can I remove it? I thought we should give a 180-degree RF pulse. But when I give a 180-degree pulse, what will happen? If I give a 180-degree pulse. No. Peace be upon him, which is the idea that something that was lying on its face is now lying on its back. Look, I'm talking about the 90 degrees, right? For sure, relaxation happens after the 180. What happened? You said the 180 is effective. The protons are starting to regroup again. Thank God the phase is visible. Look here, they started to spread out. Here, at 180 degrees, they begin to come together again. So why? Don't you record the signal while relying on it? I mean, why not record the signal right after giving the 180? They told you that if you recorded the signal at that moment, first, your signal, when the protons are in the magnetic field, its strength weakens, so the signal will be weak. That's number one. Number two, you have an effect that you want to eliminate. You just want to get the T2 image, which is solely based on the T2 constant difference in T2 constants between different tissues. Now come here, so you can imagine what's happening. Look, my dear sir, I gave the 90-degree pulse, and the protons went down in the X and Y. See, as soon as they start to spread out, I gave the 180. Now, when I gave the 180, what happened? When the 180-degree refocusing pulse is applied, it flips the protons, meaning they return in the opposite direction. They start to gather as soon as they reach the maximum gathering point, which is where your signal begins to be collected. Once they reach the maximum point, which is the highest magnetic strength, your signal starts to be recorded. From 90 to 180 degrees is half of the echo time. And from 180 to the echo time is the second half. The time from 90 until the recording is your echo time, and from 90 to 180 degrees is the first half of your echo time. When you apply the 180-degree pulse, they start to gather. Why do they gather? The answer is that when you flip them, the proton that was lagging now leads, and the proton that was leading is now the last one, because you flipped their direction. So, one of the protons that was ahead of the others is now behind them after the flip. The one who was late will start to return, and they all gather at a certain point. This point is where I perform the 180-degree pulse, which I call the refocusing pulse. I relied on my echo here based on the spin motion of the protons. At this time, I named it the spin echo sequence. The spin echo sequence consists of a 90-degree pulse and a 180-degree pulse. The gradient sequence removes the 180-degree pulse, leaving only the 90-degree pulse. However, when we talk about the gradient, we will discuss that you will receive a signal based on the homogeneity in the magnetic field and the spin. Relaxation. which is referred to as the dephasing that occurs. So you do not apply a 180-degree pulse in the gradient, but you do apply a 180-degree pulse in the spin echo to eliminate the effects of homogeneity in the magnetic field and the spin-spin relaxation that occurs. All right? Now, regarding who precedes whom and all that, look here. Look. See what this is? Here is the rabbit. This rabbit was the first one, the first proton that raced with me in the defensing. And the turtle, or whatever it's called. There is no God but Allah. Turtle. The turtle is done. My mind is done. When you give the 180 pulses, the one that was racing comes closer to the turtle or this turtle, so both meet at a certain point. All right. What happened? I gave the 190 pulses, 90 pulses. I'm sorry. The defending happened. Okay. When you give the 180, it starts to flip. What flips? The state of the proton that was racing becomes the one that is delayed, and the one that was delayed becomes the one that is racing. All right. In this case, what happens? The fast one that has a high frequency will catch up with the other one. So both gather at one point where I take its signal. Is that clear, my dear? This table illustrates the difference between T1 and T2, showing that fat has a value of 52 in T1 and 80 in T2, which means it takes a shorter time for decay in transversal magnetization, and a longer time of 52 for relaxation in longitudinal magnetization. In transversal, it takes 2.5 times longer for relaxation in the kidneys, which is 550. You will always find T2 constant, and it is always less than T1 constant, except for water, where both are the same. We have discussed the concept of spin echo and its reliance on the 180 refocusing pulse, and how it is important for the homogeneity effect in the magnetic field, which is why it is called spin echo sequence. There is an important point to note. I choose a T1 image based on long TR, long TE, short TR, and short TE. So if I take a sequence based on long TR and short TE, what will this sequence be called? Long TR will eliminate the effect of which and enhance the effect of which. The long TR will eliminate the effect of the T1 constant, the longitudinal magnetization, right? You will confirm this statement, and the short TE will eliminate the effect of the transversal magnetization, correct? So in this case, what does your signal depend on? It depends on the proton density, on the number of protons present in the different tissues. Therefore, if you use LTR and LTE, you are talking about T2. Why LTR? 2. Remove the effect of the T1 constant. Why remove LTE? Why LTR and LTE? I got confused. Sorry. Again, T2, T1. I have a T1 image with short TR and short TE, and a T2 image with long TR and long TE. I use short TR to maximize the difference between the longitudinal magnetization in different tissues and short TE. Adjust the TR precisely to maximize the difference between the various tissues, and my condition is TE. Why? To eliminate the effect of T2 constant in different tissues, I will use long TR to eliminate the effect of longitudinal magnetization and long TE to distinguish the difference between tissues in T2 constant. So what will I do? I will take long TR and short TE. Long TR will remove the effect of T1. And what about the police? Whose effect was removed? The effect of T2. So in this case, the signal difference that you receive will depend on whom? On the number of protons present in the different tissues, which is what? It is the proton density sequence. So I have sequences like the spin echo sequence, the T1 sequence, the T2 sequence, and the proton density sequence. These three sequences depend on the sequence and the T1 sequence and the T2 sequence and the proton density sequence. These three. Relying heavily on the values of TR and TE, both involve a 90-degree pulse and a 180-degree refocusing pulse. There are some issues with the doctors regarding what I mentioned. This is an example illustrating the difference between T1 and T2. You will see the fluids here appearing in white, and here they start to appear in a darker color. The CSF here is bright, while the CSF here is dark. The bright area here is more pronounced in T1, while this area is not bright in T2. T2 imaging involves using a long echo time and a long repetition time, both of which are greater than 2000 milliseconds. This is a key parameter in MRI scans, ensuring that the images captured provide the necessary contrast and detail for accurate diagnosis. That's the essential information. One thing you all need to know is something called free induction decay. Paul, what is this free induction decay about? It says that when the signal is in transverse magnetization, if I place my receiver coil in this direction, the more my protons are decaying, the signal starts to give you a signal called free induction decay. What happens is that my mx and my are continuously decreasing. The closer you are to your receiver, it's as if you are giving a high amplitude to the signal. Look here, it's spherical. I am now standing these protons. The user receives the signal, and at the same time, its value decreases as it rotates, as if it is exactly far from the user or the coil. The whole idea is to convey that the process of decay is represented by a specific signal called free induction decay. The amplitude of the signal decreases over time. Why? Because the strength of mx and my keeps changing over time. So the curve that represents this is called free induction decay. FID. The free induction decay that occurs is overcome by using a refocusing pulse at 180 degrees, which gathers the protons, removes the phase, and creates a new phase for the protons. We are repeating, and again repeating, 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 repeating. This is about the T2 star, or free induction decay pulse. And this is the T2, which is the actual curve that depends on the T2 difference, or T2 constant difference between tissues. In the gradient, We are discussing the idea that I am not concerned with having a refocusing pulse present. Rather, I want to work on. The concept of this idea is fundamental to understanding the broader implications and applications in various fields. The quick brown fox leaps gracefully over the lazy dog, demonstrating its remarkable agility and impressive speed in a captivating display of natural athleticism. You tell me like this, with the 90-degree pulse, this is my RF. Now I will draw my sequence with the 90-degree pulse. First, I need to accept what I will do with the 90-degree pulse. Great, you got it. And what will I do with the 180-degree pulse? I will apply a selection gradient because I will target a specific slice. I will place the selection gradient here and here. You need to activate the selection gradient in any RF pulse you apply. I will activate it and keep it on. I won't turn it off. As soon as you apply it, you return again. After the selection gradient, there is the phase encoding gradient, which consists of the different degrees we talked about, which depend on the matrix rows present in the matrix. All right, so now I will give you 90 along with the phase code.